tell us a bit about, there's in recent years, YOLO style architectures, which
Mhm.
YOLO is like when you're a college student, I guess going on spring break, it's you only live once.
Yeah,
But with these architectures, it's you only look once. So there was this
yeah.
original paper a number of years ago on YOLO architectures, but I think you probably know enough about this that you can even go back before YOLO and tell us kind of how object detection has worked historically at a high level, and then what these YOLO architectures changed, and why those are like the dominant architecture for object detection today.
Yeah, even before like deep learning, there was people were doing object detection, but they're using something like histogram of gradients plus maybe some linear support vector machines on top of that to do whatever they need to do. But of course, with classic ML, like you have to hand engineer all those features, which is a pain. But then right around 2014 is the AlexNet moment happened in 2012, and obviously people started going crazy over neural nets and deep learning. But 2014 was like one of the earliest um, object detection, uh, the earliest deep learning based approaches to object detection. That was called RCNN. So that's region based convolutional neural network. So that one, like you would take in an input image, then you'd extract a bunch of what they called region proposals. Then you'd use some CNN to do some type of feature extraction and then classify whatever the regions are, right? Um,
Yeah,
and
CNN being
then, yeah,
convolutional neural network, which
yeah,
was like, and we could actually, so just to like really quickly digress,
mhm,
um, in natural language processing, which is my expertise really, we have now gone completely from using recurrent neural networks, RNNs or LSTMs, long short term memory networks. We now are completely in this transformer world where we're like, wow,
mhm,
transformers are way better because they can take into account like all of the context in a given piece of language. There are trade offs that people are working on where like the compute complexity squares polynomially
yeah.
when you're working with these transformer architectures. But is uh, are CNNs still used a lot in machine vision today, or are those also moving over towards transformers?
I think they're still being used for sure, but transformers have crept into the computer vision world as well. So there's a lot of new transformer based kind of architectures for detection and classification tasks as well. So yeah, it's definitely creeping into there. I haven't done too much research into that. Like I've only really been doing deep learning for about a year, and so this is on my long list of things I need to figure out. But it's a
Nice.
good
Well,
list to
it's just
have.
a quick
Yeah,
digression because yeah. So
yeah.
you're confirming for me that transformers are being increasingly
Mhm.
used in machine vision, but CNNs are also still being used. So that is a bit different from natural language processing, where like I
Yeah,
don't really know anyone who's using RNNs anymore. But anyway,
yeah,
so
yeah,
CNN. So you're talking about RCNN in 2014 being the first
yeah.
big deep learning architecture for object detection, and then I started interrupting you.
Yeah, yeah, and then there's improvements on RCNN. There's fast RCNN, faster RCNN, um, and it, the thing with these type of methodologies is that you needed to do two passes through your neural network to classify and then get the bounding box coordinates. But then YOLO came along, and YOLO kind of just changed all of that. So instead of having to have two passes through a neural network, you only look once. You only have to look at the image once and do one pass through the neural network.
Mm-hmm.
And so they took off in popularity because their impressive speed and accuracy. Um, so I don't know if you want to quickly just talk about kind of like the anatomy of an object detection model. Like you've got the backbone, neck, and the
Yeah,
head, right?
yeah.
So the backbone is where we would extract features from an input image, and typically that's done using a convolutional neural network, and then it's capturing kind of hierarchical features at different scales. So lower level features like edges and textures are being extracted in the more shallow layers, and then as you get deeper, you get more higher level features like more kind of semantic type of information. And then the neck is the part that is connected to the backbone and head, and kind of does that actual classification and bounding box prediction for you as well. Um, yeah, so YOLO came around in the paper was published in 2015, but it was presented at the CVPR conference in 2016, and it just took the world by storm with how fast it was, and it smashed uh, the previous state of the art. So MAP, mean average precision, that's the metric that we look at when we measure how good a object detection model is. If you want to talk about that, I can give it, at
Yeah,
a high
let's
level
talk
what it
about
is.
that. I just really quickly, I'm gonna get you to elaborate a little bit on CVPR. So you've mentioned that you said
Yeah,
how with your Deep Learning Daily podcast, you're going to be there at the time of recording in the future, and so probably by the
yeah,
time this episode's released, it'll be in the past. But you're
yeah,
going to the CVPR conference, which is it's the premier computer vision conference, right?
yeah. Computer vision, pattern recognition, but really it's like a deep learning uh, type of conference. And yeah, one of the well-known ones, kind of up there with Neuro Ips and what's the other one? ICML.
ICML,
Yeah,
yeah.
big conference.
But yeah, and I guess this one skews a bit more towards machine vision applications than those other
Yeah,
two necessarily
yeah,
would. Super cool. So yeah, so you were saying, yeah, these kinds of big breakthroughs like YOLO get published in the CVPR proceedings, and then you were about to tell us about MAP, which is a key metric for assessing the quality of a detection model's output. So I guess like there's these two kinds of trade-offs that you're trying to work through. Like you want it to be fast. And so you've been talking about how from RCNN to fast RCNN to faster RCNN, obviously they're going faster, but then YOLO was a big step change because it didn't require these multiple passes. It was able to, in a single pass, be able to both identify where objects are in the images as well as classify those images, which is kind of a mind-blowing thing to me. Like you described it there through the backbone, neck, and head anatomy, but like because I haven't spent enough time with it myself, it's still something that like I'm kind of mind blown by. But so obviously speed is a key consideration, but then simultaneously another big consideration is accuracy, of course. And so I guess map is like the key way to measure that accuracy.
yeah, yeah. And it's based on precision and recall, so familiar terms to classical, data science folks. So MAP gives you kind of a balanced assessment, and then there's another assessment that you would call IOU, that this intersection over union that tells you how good your bounding boxes is. And then there's another thing in there in object detection that we call non-max suppression that helps filter out redundant bounding boxes that you might get during training. But so just kind of breaking it down, right? So we all know what precision is, right? It's just the model's ability to make an accurate positive prediction, right? And then recall is the number of actual positive cases that the model correctly identifies, right? So precision, you can think of it as like a sharpshooter, and it's hitting the target accurately. And recall is like a detective who is catching all the suspects in the crime. So there's always that trade-off between precision and recall.
Nice.
That's why we have that
I love that
precision recall
analogy.
curve. Yeah,
That is easily the best analogy I've ever heard for explaining precision and recall. And maybe now, like, I'll be able to remember it and I won't have to keep going to Wikipedia every time someone's like, I'm like,
yeah,
yeah, I know what that is. Everyone's always talking about that. I, of course, know what it is.
yeah. Dude, trust me, like I get it confused all the time. Don't ask me the formula, but I don't know what the formula is off the top of my head. But so what mean average precision does is, we have the precision recall curve, and map mean average precision is calculating the area under the precision recall curve to give us like a balanced assessment for how good this uh, particular model is. So what it does is it's incorporating the precision recall curve, like I mentioned, and plots precision at against recall for different thresholds, right? So when you do it this way, you get kind of a more balanced assessment, because you're considering the area right under the curve, and then you got to think about the multiple objects that are you know being detected in an image. So map is able to handle multiple object categories by calculating each category's average precision separately, and then taking the average across all the categories. Right. So it's
Right.
measuring average precision for the object. You do that for all the different objects, and then you average that, and you get the mean average precision. Um, and then there's another concept to measure how good the object detection model is, intersection over union, and this just
Mhm.
measures the the quality of the predicted bounding box, by comparing kind of the intersection and union of areas.
Got it. So,
Yeah.
so the map, the mean average precision, is for figuring out once, like within the bounding boxes, how accurate are the predictions, and the IOU is more about how accurate are the placements of the bounding boxes.
Yeah. Yeah. Exactly.